So good morning, my dear students. Welcome to the online classes. In last class, we are discussing the rotating field type synchronous generator and rotating armature type synchronous generator. Out of these two systems, we are concluded that the rotating field system is suitable for high power missions. That's why in our generating stations, we are used the rotating field type synchronous generator to produce or to generate high voltage. Is it? So now, what are the advantages due to the rotating field type or stationary armature type synchronous generator means? First thing is there is no problem regarding to the provision of insulation. Is it? See, it is very easier to insulate a stationary winding for high voltage because of if the armature winding is rotating, if high voltage is generated in that rotating armature winding, the insulation for that high voltage is in huge amounts. The thickness of providing of insulation is very large. If it is rotating with a certain speed, what happens? The insulation can change their position. It is not fixed. That's why the insulation may be deteriorate during the lifespan of the mission. That's why at certain period of lifespan, what happens? The insulation damage takes place. Finally, short circuit occurs between the armature windings. That is due to the rotating armature winding. So, but we are using stationary armature. We have to protect the insulation for high voltage armature windings because of the position is fixed. There is no rotation. That's why the provision of insulation for stationary armature winding is easier. That's why we will prefer the stationary armature or rotating field type synchronous generators. One more advantage is the armature winding is stationary. The output voltage is collected across the stationary winding. Is it? That's why it is directly connected to the load. There is a provision of direct connection of load. Direct connection means there is no need of slip rings and brushes. If it is a rotating armature winding, as in case of DC generator, what happens? Slip rings and brushes are required to collect the currents from the rotating armature winding, to collect the output from rotating armature winding. But here it is stationary armature. That's why across the two terminals of the armature winding are, it is three phase. That's why three terminals of the armature winding, that load is directly connected without usage of slip rings and brushes. One more thing is that this is the second advantage. There is no need of a large number of slip rings and brushes. One more thing is that, see here. This is stator. Stator means armature winding is there. This is rotor. Rotor means field winding. Field winding means this field winding is employed on field poles, north, south, north, south. These are called alternating poles of a synchronous generator field system. Is it? So field winding is mounted on this or bounded on this field poles. And when DC supply is provided to this field winding of poles, what happens means direct current flows through the field winding of these field poles, north, south, poles. When current flows through the winding or conductor, what happens? A current carrying conductor established magnetic field. We are already discussed in our EMF subjects. Is it? So magnetic field is developed means magnetic flux is there. Is it? That magnetic flux is called field flux. That's why this rotating field system develops the required flux to produce voltage in the armature winding of stator. So here field flux is produced due to the when DC supply is provided for this field winding of the field poles. Is that it? How the DC supply is provided means here DC supply means voltage. DC voltage we are provided. So by using DC shunt generators and batteries we can subjected DC voltage. Then when DC voltage is provided for this field coils or field windings, a direct current flows. But in order to flow the current through this field winding, we require slip rings and brushes because of in case of a synchronous generator or alternator, we are using rotating field system in our generating stations. If it is a rotating system, we are not given directly the current. That's why slip rings and brushes are required. That's why here for rotating field system, slip rings and brushes are used to provide a direct current to the field coils for the production of flux. For the production of field flux. Is that right? So that's why here field flux is produced by subjecting the DC supply through slip rings and brushes. One more important thing here, if DC voltage is provided, what happens? DC current flows to the field coils. If DC current flows to the field coils, static magnetic field is produced. That's what we are discussing in our EMF subject in magnetostatics. Is that steady flux means it is a stationary. That means the magnitude and direction of magnetic field or flux does not vary with respect to time. Stationary flux. But here in the stator armature windings are stationary. Then where is relative motion? Is that it? Now see here. Actually the flux is stationary flux. It is good, right? But the field system, field poles are not a stationary one. It is rotating in a clockwise direction like this see here in this figure. That means here the total field system is rotating. That's why here the developed direct flux or steady flux can also revolving in a particular direction. That's why this flux will become as a revolving magnetic flux, or this field is called a revolving field. Is that right? When this revolving magnetic flux is interacted with this stationary armature conductors or winding, the conductor cuts the revolving flux. Then there is a relative motion. That's why EMF is induced in the stator winding. That's why here the static flux only here, not only here static flux it is, steady flux it is a revolving flux. Why? Because of this rotating field system is there. This field system is rotated by the prime mover turbines. That's why this field system is a revolving flux. This is a static flux, a stationary flux, stationary magnetic flux or steady magnetic flux, revolving. Steady magnetic flux are revolving. Is it right? So that's why this revolving magnetic flux, there is a relative motion between static conductor and revolving magnetic flux, then EMF get induced across the stator winding. Is it right? So now we will go for constructional details of three-phase synchronous generator. Three-phase synchronous generator means it is always rotating field type synchronous generator or stationary armature type synchronous generator. Why? Because of that type of synchronous generator can be used in our generating stations to generate high power or high voltage. Is that right? That's why here construction of three-phase synchronous machine means this is rotating field type or stationary armature type of synchronous generator. So as usually, in order to construct any electrical mission or any energy conversion mission, it has essentially two parts. What are those? Means stator and rotor. Is that right? For every electrical mission which has stator and rotor. Is it? Stator means which is a stationary part, rotor means which is a rotating parts. Which is a rotating part. In case of a three-phase synchronous generator, The stator is a armature winding here. Is that stator is nothing but a stationary part. In that stator, armature winding is there. That means the conductors are located in the stator of the three-phase synchronous generator. When conductors are located means when these conductors are interacted with the magnetic facts, what happen? EMF get induced in this stationary armature winding or armature conductors. Then the output is collected. The output is subjected across the stator terminals, or the load is directly connected across the stator terminals. Then how the stator is constructed means mainly the stator is having stator frame. See here, now this is the stator of three-phase synchronous machine. Mainly which has stator frame. This is a frame, and this is a stator core here. It is. This is stator core here. Core of the stator. Finally, it is a armature slot. Slots are provided for the armature to accommodate the armature windings. Armature windings are the conductors. Generally, we are using copper conductors for the armature winding. Anyway, the stator is constructed with the stator frame, stator core, and armature slots for armature winding, or that is the stator winding, and cooling arrangement are also required. Cooling arrangement is necessary to cool the stator while it is running. While the machine is running, heat is developed. When heat is more, what happens here? I square R losses are also more. When I square R losses are more, efficiency is less finally. That's why to avoid that problem, cooling arrangement is provided for stator and any type of arrangement. But anyway, cooling arrangement is minimum requirement for any construction. Is it? And also, at every electrical machine, the core is laminated because of the core is having eddy currents. The current flows through the core structure are called as eddy currents. This eddy current provides eddy current losses. Is that right? If these eddy current losses are more, the efficiency of the machine can be reduced. That's why to avoid this problem, what happened? The stator core is laminated with steel. The stator core is laminated with a high-grade silicon steel. With a high-grade silicon steel to reduce hysteresis and eddy current losses. To reduce eddy current losses, we are provided laminations. Is it a thin laminations? And to reduce hysteresis losses, we can use the high permeability material, that is high-grade silicon steel. High-grade silicon steel reduces the hysteresis losses, and the laminations are reduces the eddy current losses. Finally, the core losses are reduced by the silicon steel laminations, high-grade silicon steel laminations. And the stator frame, this stator frame can protect the whole stator. The stator frame can protect the whole stator. Stator means armature and stator core. Is that right? This stator frame is manufactured with cast iron for smaller machines, small size machines, and welded steel type for large size machines. This frame is manufactured with a cast iron if it is a small size machine, and it is manufactured with a welded steel type, which is a large size machine. Is it? And this is about the structure of stator. Stator frame, stator core, and stator windings. So stator winding is armature windings, which are stationary windings. Is it? So here these are called armature slots like this. These slots are provided to accommodate the armature windings. These are stationary. Armature windings are stationary. These are not rotating. That's why these are called stator windings. And these stator windings are manufactured with the copper material. These are copper conductors. And next one is rotor. What is meant by rotor? Rotor means which is a rotor, rotating system. Rotor means which is a rotating system. So in a three-phase synchronous generator, the field is rotating. Is that the produced field is rotating by using turbines. With the help of turbines, the field is rotating. That's why the field system, the field is mounted on the rotor. That's why the field system is called as the rotating part here. Is that it? So here in the three-phase synchronous generator, we are used two types of rotors. Depending upon the nature of poles in the rotors used in the synchronous generators are classified into two ways. Those are salient pole type rotors. What are those means? Salient pole type rotor. And the second one is non-salient pole type rotor. Non-salient pole type rotor. Is it? So then first one is salient pole type rotor. What is mean by salient pole type rotor means in this rotor, the poles are projected out from the rotor surface. When the poles are projected out from the rotor surface, that type of rotor is called salient pole type rotor. Salient pole type rotor. See here, this is rotor. This is total rotor, and these are poles, south, north, alternating magnetic poles. And these poles are projected out from the rotor surface. This is the rotor surface. This is the rotor surface. That's why here the poles are projected out from the rotor surface. That's why this type of rotor is called as the salient pole type rotor. If the poles are not projected out from the rotor surface, the poles are located on the surface of the rotor like this. North pole, south pole, north pole, south pole. Is it? So if the poles are projected on the surface of rotor, such a type of rotor is called as a non-salient pole type. Non-salient pole type synchronous generator or non-salient pole type rotor. Is it? So now we will see what is the nature of a salient pole type rotor. This is a salient pole type rotor. That means here what happened? The poles are projected out from the rotor surface. Is it? If we can observe, all poles are fixed to the rotor. This is rotor. Why it is rotor? This part can be rotated with the shaft of rotor. This shaft can be rotated by taking mechanical power from the shaft of the turbine. When turbine shaft, rotor shaft are coupled together mechanically, then mechanical power is transferred from turbine to the rotor of this type of generator. Then what happens? This rotor rotates. When rotor rotates means what happens? This is salient poles. These poles south, north, also rotate. Because of these poles are bolted to this rotor. Is it? And one more thing is that all these are steel poles. Why we are using steel pole means to reduce hysteresis and eddy current. Is it? We are providing the poles are built up of thick steel laminations. What is the need of thick steel lamination? Means to reduce hysteresis and eddy current losses. By using steel, hysteresis losses are reduced because of this high permeability material, and by using laminations of steel, we can reduce the eddy current losses. Finally, this pole core losses are reduced. Then efficiency is improved. Is it? One more thing is that the field winding is mounted on these pole cores. These are the poles south, north, and this is the field winding. This is the field winding which is mounted on these poles. When DC supply is provided for this field coils, these are nothing but windings or coils. When DC supply, this is the DC supply provided to the field coils through slip rings. These are the slip rings, rectangular brushes. These are brushes and slip rings. Is it? Through slip rings or brushes, the DC current flows to the coils. When current flows to the coils, required magnetic flux is set up. Is it? And this is this total magnetic flux is rotated with the rotor. That's why which is a revolving magnetic flux. Which is a revolving magnetic flux. When this revolving flux cut the stationary armature conductors, stator armature conductors, EMF can be generated in the stator. Then voltage can be collected across the stator windings, 3 terminals. Why? Because of it is 3 phase. Is it? So that's why here this is the nature of a salient pole type rotor. If we can observe one more important nature is the pole face has been given a specific shape. Is it? So this is the specific shape. So due to this specific shape, what happened means due to this specific shape. Is it? This is specific shape. Due to this specific shape, what happened means the diameter is large and the axial length is small. The axial length is small, but the diameter is large. Axial length is small, but diameter, see here, this is total diameter is large, but axial length is small. Is it? So this is the nature of a salient pole type rotor. While coming to non-salient pole, this non-salient pole means what happened earlier we are already discussed. The poles are located on the surface of the rotor. That's why this is called, this type of rotor is called non-salient pole type rotor. Is it? North, south, north, south. So with this arrangement forms a cylinder shape. This arrangement forms a cylinder shape, and for this type of construction, a solid smooth steel we can use. Steel we can use. That's why this is a simply smooth solid type of steel type of cylinder. Smooth solid steel type of cylinder it is. What happened here in this cylindrical structure? Slots are provided like this. See here. These are the slots. In this slots, field winding is mounted. These circles, dots represents the field winding. Is it? When a DC supply is provided through slip rings or brushes, current flows to the field winding. Then what happens? What happens? Field flux is produced. Field flux is produced. That's why required field flux is established in this rotor circuit. Okay? When conductors touch this rotating flux, revolving flux, is it? Then what happens? EMF get used in the stationary armature windings. Is it? Now, if you can observe here, these are slots. In this, these are only these are slots. These are. In these slots, field coils are employed, but these are unslotted portions. These are unslotted portions. North, south, and north, south. These are called unslotted portions. These unslotted portions are called poles, magnetic poles. Is it? So here, that's why what happened here means diameter reduces. Here, the poles are located on the surface of rotor, not projected out from the rotor surface. Due to this type of arrangement, this type of construction, the diameter can be reduced and the axial length can be increased. Due to the increasing of axial length, this type of rotor maintains constant air gap between stator and rotor. If there is a constant air gap, what happened here? Constant air gap means reluctance also uniform. Then what happened? There is no loss of flux. Maximum flux is cut. When rate of change of flux linkages are maximum, induced EMF is also maximum according to Faraday's laws of electromagnetic induction. That's why this type of rotor can provide uniform air gap. Is it? So that's why this type of rotor provides so many of advantages. What are those? Which can provide constant air gap between stator and rotor. Due to that, what happened? Your reluctance also uniform. That means what happened? There is no loss of flux. The strength of output can be increased. One more thing is that So due to this, what happened? The total weight can also reduces. The total weight can also reduces and also mechanically balanced here. In case of salient pole type of rotor, what happens? This is air gap. This is air gap. This is in this portion air gap is more larger. This portion air gap is less. Air gap is not uniform in salient pole type, and also mechanically imbalance takes place in salient pole type rotor. But in case of non-salient pole type rotor, what happened here? Air gap is uniform at all the places. This place, this place, this place, this place, and here also. Mainly we are concentrating these areas, outer surface of rotor. Non-salient pole type air gap is not uniform. In non-salient pole type air gap is uniform. That's why what happened? Reluctance also uniform. The flux strength is no, EMF also. And also here what happened? This is mechanically balanced because of diameter is less. And uniform air gap maintenance. What happened? Mechanically balanced. That's why this type of arrangements limits the speeds. When it goes to overspeed, it can act as a flywheel. Due to flywheel, what happened? These field windings change their position and short circuit. So to avoid that problem, the speed can be limited in this type of rotor. All these are advantages. That's why these are mechanically very strong and these are preferred for high speed alternators ranging between 1500 to 3000 RPM. Such as high speed alternators are called turbo alternators. Generally, these type of rotors are used in thermal power plants. Because of, in case of thermal power plants, turbo alternators are required. Is it? So why? Because of that is steam with high pressure and high temperature. Due to that high pressure, what happened? Force is more. That's why the speed of the turbine also more. That's why this type of turbines used in thermal power plants. These are called the alternators used in thermal power plants are turbo alternators because of their speed is between 1500 to 3000 RPM. And this type of rotor advantage is mechanically very strong. That's why these are preferred in turbo alternators. Is it? So these are the types of rotors, and this is the total construction of three-phase synchronous generator. And depending upon these two rotor types, the synchronous generators are classified. If we are using salient pole type rotor, the synchronous generator is called salient pole type rotor synchronous generator. If the synchronous generator uses non-salient pole type rotor, the generator is called as the non-salient pole type rotor synchronous generator. If we can observe, non-salient pole type rotor is in the form of a cylinder. That's why this rotor is also called as the cylindrical rotor. And also this is in the shape of round. But in case of non-salient pole type rotor, this is a certain specific shape is there. But in case of non-salient pole type rotor, what happened here? This is round type. That's why it is called as a round rotor. Is it? So, and also it is in the form of round with a smooth arrangement. Then that's why it is called smooth cylindrical rotor. Three types of means are there for this type of rotor, and this type of rotor is very convenient for salient pole type. Is it? And advantages are also there by using this type of rotor. That's why we will prefer this type of rotor for turbo alternators, high speed alternators in thermal power plants. Is it? Thank you.